In this video, we discuss learning outcome number 4 of lesson 7.2. Here we discuss how to find the sample size necessary to estimate a population mean to a desired degree of accuracy and with a desired level of confidence. So here are some formulas. Now these are the formulas for the confidence interval for estimating a population mean in the rare case that the standard deviation sigma is known. It's the standard deviation of the population. We'll say that under certain conditions, the confidence interval for the population mean can be computed when that population standard deviation is known using these formulas. So the population mean is in between that sample mean minus the margin of error and the sample mean plus the margin of error. But this time, if we know the if we know the population standard deviation, the error is given by this. It's z sub alpha over 2, that's a z-score from our standard normal distribution, times the population standard deviation divided by the square root of the sample size. Now here's another question. We say, okay, if that's how we compute the error and that's how we compute the confidence interval, we might be asking this, like what sample size is necessary in order to have a desired error? Because maybe we know how close we need to be to that true population mean that we're looking for, and then what level of confidence are we comfortable with? If we know what level of confidence we're comfortable with and we know what we want that margin of error to be, we can determine the sample size that's necessary to achieve that. So if we know that margin of error, if we know our desired level of confidence, and we know that we're going to select our sample in such a way that it's a simple random sample, then we can just take that error formula that we saw in the last slide and rearrange it to solve for n. So if I divide both sides by z sub alpha over 2, and then I divide both sides by sigma, and then I flip both sides and square both sides, I get this. So the sample size that is necessary to achieve this error with a degree of confidence 1 minus alpha is given by that z sub alpha over 2, our critical value of z, times that population standard deviation, all divided by that margin of error that we're seeking, squared. That's going to give us a sample size. It's probably not going to be a whole number. We always want to round up because that number that we get is associated with that error. If we round up, we'll have less error than intended, and less error is fine. We just don't want to accidentally have more error. If we round down, we're going to have more error. So it does not matter what our typical rounding conventions would be. If you don't have a whole number, you always round up to that next whole number for n. So here's just a quick review of the notation for confidence intervals of population means. Mu represents the population mean that we're trying to estimate. N is the sample size, or the number of sample values. X bar is the sample mean. That's just the sum of the sample values divided by that sample size n. E is that desired margin of error. Sigma is the population standard deviation. Often it's unknown, but we're talking about the case when it's known here. And z sub alpha over 2 is the z-score separating the top alpha over 2 area from the remaining area under the standard normal curve. This is the z-score that's going to separate those values of the sample mean that are sort of typical from those that are significantly high. And when we say significantly high, we're using this alpha or this 1 minus alpha confidence level associated with that. So there's a lot more to that. If you don't remember all of that, we discussed it way back, I think, when we first started talking about z-scores. So you might want to check out that video if you don't remember how z-scores are related to these sample statistics that we're trying to estimate. I think that was in the video when we were first going over how to estimate a population proportion rather than a population mean. Okay, so here's a question. What if we don't know the population standard deviation? Most of the time we don't know the population standard deviation. So what do we do? In that case, there are a couple of things we can do. We can estimate it. We can use the range rule of thumb to estimate that standard deviation. Now remember what the range rule of thumb says. It says if you take the range and you divide by 4, that is a very rough estimate of the standard deviation. So we might use that. And remember, the range is just the maximum value in your data set minus the minimum value in your data set. It's very easy to compute. You divide by 4 and you say that's approximately equal to the standard deviation. So that's an option. Another option is to start the sample collection process without knowing that population standard deviation. And then once you've collected the first several values, calculate a sample standard deviation S, and then use that in place of the population standard deviation. Now, as you collect more values, you can improve that estimate of the population standard deviation as more values are obtained, and then you can also refine your sample size. Or lastly, you can estimate the population standard deviation using the results of some earlier study. So maybe someone else told you that the standard deviation should be this. So we can use that going forward. So you've got the range over 4 option, you've got computing it, or computing a sample standard deviation for just the very beginning of your sample, that first part of that sample that's collected, or you can just use old values that are known from previous studies. Okay, so let's look at an example. It says, assume that the standard deviation of IQ scores is sigma equals 15. And suppose we want to estimate the mean IQ score for the population of attorneys. Now, it turns out that the population standard deviation for IQ scores for the general population is 15. But if we're talking about IQ scores for attorneys, chances are, because they're all attorneys, the variation is going to be less. So that standard deviation of 15 is probably very conservative. It's an overestimate of how much variation there would be in the IQ scores of attorneys. So that means our estimate here is going to be a conservative estimate, and we might not even need as many values as we're going to come up with because our standard deviation is a little bit high. It's a little bit of an overestimate. Okay, so with that in mind, the question says, how many attorneys must be randomly selected for IQ tests if we want 98% confidence that the sample mean that we find is within 3 IQ points of the population mean? Okay, we know we want our error to be 3 IQ points or less. We know that we want 98% confidence. With those 2 pieces of information and the given population standard deviation of 15, which is going to be conservative for this group of population of attorneys, we can find out how many attorneys we would need to estimate that population mean to within 3 points with a 98% confidence level. Okay, so first we'll just state the formula and everything that's given. So we know sigma, that was given. We know the margin of error that we're seeking, that was given. We don't know z sub alpha over 2, but we do know the level of confidence. And with the level of confidence, we can find a z sub alpha over 2. So it looks like all we need to do is find z sub alpha over 2, plug everything in, find out what n is, and then round up. So we've got a 98% confidence level. We've got a population standard deviation of 15. And that error is 3 IQ points. We don't want to be off by more than 3 IQ points in either direction. We need to, the only thing we need to compute is that z sub alpha over 2, as I just said. So I've got a little issue with my PowerPoint here. It's okay. The graph will show up in a little bit. So it says compute z sub alpha over 2. The first thing we notice is that we've got a 98% confidence level. If I know that I have a 98% confidence level, I can find alpha. Alpha is the complement of that. So alpha is 2%, but we write it in decimal form, so that's 0.02. Now, whenever we're constructing a confidence interval, that confidence level tells us what that area should be in the middle, either under the standard normal distribution when we know the population standard deviation, or under the curve representing that student t distribution when we don't know the standard deviation. But we're still looking for that. If we have 98% confidence, we're still looking for that 98% of the area in the middle. So alpha is the area in the tails, in both tails. In order to find the area in one tail, we've got to split it. So we take alpha over 2. So we've got 2% of the area in the tails, you got 1% in the left tail, 1% in the right tail. Now we want to sketch a standard normal distribution with 98% of the area in the middle. And that's where that 98 came from. That was supposed to be with this image of the standard normal distribution. Okay, so we're trying to find this z-score over here that separates that top 1% of the area from that bottom 99% of the area. So we find the area to the left, which is the 98% plus the 1%, which is 99%, or the true area is 0.99, got that decimal. And then we find z sub alpha over 2, and we've actually got a couple of options. We can use Excel, or we can use table A2, or you can use other calculators or technology to find this z-score. So let's use Excel. With Excel, I got 2.33. Let's show how we would do that. Now remember, when you use Excel for something like this, oops, looks like that's what I already did over here. Let's clear all this. If you are trying to find a z-score associated with an area, you want the standard normal function, but you want the inverse of that. Because normally we give them a z-score and we ask for an area. This time we want to give them an area and ask for a z-score. So we want the standard normal distribution function. So we'll type equals NORM for norm, S, that's standard normal, and then INV is the inverse function. Open parentheses, and then in the parentheses you should put the area to the left. I want that area to the left to be 0.99. And so I get that 2.326. And if I'm rounding to 2 decimal places, because that's what we have in table A2 in our handout from Mr. Triola, we get a z-score of 2.33. So it's 2.33. Or you can use table A2 and you get 2.33 as well. So remember, if you've got an area and you're looking for a z-score, you look for the area 0.9900 in the body of the table, because the areas are in here and the z-scores are on the outside edge, remember? So I'm looking for 0.99 and I don't see it, but I see something that's very close. I've got 0.9901. There it is. There's my area. I want to know, what is the z-score that goes with that? Well, the first part of the z-score is right there. Z equals 2.3. This is 2.30. The area to the left of 2.31, 2.32, 2.33. So the closest one we have is this 2.33 from table A2. So go back to our PowerPoint and we say, yes, that's what we got. Either using table A2 or Excel, we get that z-score. Okay, now we've got the z-score, that critical value of z. We've got the standard deviation of the population, and we have a desired margin of error. To substitute all those in, and we get n is equal to 135.7. Now we can't well, I guess we could give 70% of an IQ test, but we wouldn't actually be able to use that. We need to give a whole number of IQ tests and then analyze the data. So we're gonna have to round up to 136. So this is how I would interpret this. To estimate the mean IQ score of all attorneys to within 3 IQ points with a 98% level of confidence, we need a simple random sample of at least 138 IQ scores of attorneys. Now, when we do that, we're going to come up with a confidence interval, and the margin of error is going to be no more than 3 points. And what we'll be able to say is that we'll have 98% confidence that the true value of the mean IQ score of attorneys lies within that 6-point range, because the margin of error is plus or minus 3. So we're going to be able to say with 98% confidence that the true value of the mean IQ score of attorneys lies within that interval. So that means if we did this 100 times, 98 out of 100 times, the mean IQ score would be in the interval. And that's a very good thing. So that's how we do that. I will see you in the next video to discuss how we find a confidence interval in the uncommon situation in which the population standard deviation is known.